This section will cover the hyperparameters that you need to know. Our first hyperparameter is the number of epochs. An epoch equals one full pass through the entire training dataset during model training. It's a complete cycle where the model has seen every training example exactly once. Looking at this visual representation, we see our training dataset. Each row represents a training example. Realistically, this table would include thousands or millions of rows in the real world. But when we complete one full pass through all of these examples, going through every row, we've completed one full epoch. The model will typically train for multiple epochs, sometimes even many epochs, seeing the same data repeatedly, but learning different patterns each time as its parameters adjust. The number of epochs is a hyperparameter that we set before training begins, and it determines how many times the model cycles through. Now let's examine another hyperparameter called batch size. Batch size is the number of training examples that the model processes before updating its weights once. So let's walk through how this works. Here we have our training data represented by 12 examples, numbered 1 through 12. Obviously, in a typical training data set, you would have many more examples than this, but this is just for illustration purposes. Rather than processing all of these examples one at a time, or waiting until the end of the entire training data set to update our weights, we group them into batches and then update our weights after each batch. So in this case, let's say we're using a batch size of 4. We take the first 4 examples, we group them together as batch 1. The model processes all 4 of them, calculates the loss across the entire batch, and then performs weight update number 1. Next, we move to batch 2, which contains examples 5, 6, 7, and 8. Again, the model processes all 4, calculates the loss, and performs weight update number 2. Finally, we do the same for batch 3 with the remaining examples, and then we perform weight update number 3. Notice that this counts as one full epoch. And with 12 training examples and a batch size of 4, we end up with 3 weight updates per epoch. The batch size directly determines how many weight updates occur during each pass through our training data. Larger batch sizes mean fewer updates per epoch, while smaller batch sizes result in more frequent updates. This batching approach balances computational efficiency with learning stability, and so choosing the right batch size is an important choice. Now let's examine learning rate, which controls how much the model's weights are adjusted during each update step. It is an important hyperparameter because it directly affects how quickly and effectively the model learns. To understand, let's look at 2 visualizations of a loss landscape. On the left, we see an example with a high learning rate of 0.1, which results in large steps down the loss surface. The green path shows the model updating its weights to minimize loss, starting from the same point at the top of the surface. The model moves quickly, but the large jumps can cause it to overshoot or kind of zigzag around the minimum. So this can speed up training, especially at first, but it can also increase the risk of missing the optimal weight values or causing unstable convergence. On the right, we see a low learning rate of 0.01, which results in smaller and more controlled steps, so the model adjusts its weights more gradually, allowing it to follow the loss surface more precisely. This makes training more stable and less likely to overshoot good solutions, but it also means that it may take longer to converge. So this represents a key trade-off in training. Too high and the model may converge quickly, but erratically. Too low and training becomes stable, but potentially very slow. Now let's see how different learning rates actually behave during training by examining loss curves over time. This graph shows loss versus epoch for 4 different learning rate settings, and the patterns reveal important insights about how this hyperparameter affects learning. So let's start with the green line, which represents a good learning rate. We see a smooth, steady decline in loss from around 0.9 down to near 0 over about 40 epochs. This is the behavior that we want. It's consistent improvement without dramatic fluctuations. The blue line represents a low learning rate. Notice how it starts at the same point, but it decreases more gradually. Even after 100 epochs, it's still around 0.1, making steady progress, but slow progress. This confirms what we discussed earlier. Low learning rates are stable, but they require more time to reach optimal performance. The red line represents high learning rate. Initially, it drops quickly, which might seem promising, but notice what happens around epoch 60. The loss starts to increase again. This demonstrates the overshooting problem that we mentioned, where large steps can push the model past the optimal solution. Finally, the yellow line shows a very high learning rate, and this is where things become definitely problematic. The loss oscillates wildly, jumping up and down throughout the training. At some points, it reaches 1.4, which is even higher than where it started, and this erratic behavior indicates that the learning rate is just way too large, causing the model to bounce around without ever settling into a good solution. So this visualization demonstrates why learning rate selection is so crucial. Too low and training is inefficient. Too high and training becomes unstable or even counterproductive. Now that we've covered how learning rate controls the size of weight updates, let's look at another important hyperparameter that helps models generalize better to new data. Dropout rate is the fraction of neurons that are randomly turned off during training. And the goal here is to improve generalization. You can think of it as intentionally handicapping your neural network during training so that it becomes more robust and is less prone to just memorizing the training data. It's more able to learn the underlying patterns of the data. Let's see how this works in a diagram. On the left, we have a neural network in its normal state with all neurons active and participating in the computation and in the training. Notice we have an output layer and we've got 2 hidden layers and we apply the dropout here, let's say with a rate of 0.3, and something interesting happens. On the right, you can see that some neurons in the hidden layers have been randomly turned off, shown here in gray. In the first hidden layer, 1 out of 4 neurons is disabled. And in the second hidden layer, 1 out of 3 neurons is turned off. So you notice that the input and output layers remain completely active because dropout is applied only to the hidden layers. This random deactivation forces the remaining neurons to work harder and prevents the network from becoming too dependent on any single neuron. It's kind of like training a team where different players sit out randomly during practice, and so the team kind of learns to function well regardless of who is available, just as a kind of a silly analogy. The result is a model that can generalize better to new unseen data. So remember that point for the exam. Another important hyperparameter is L2 regularization strength, which controls how much penalty is applied to large weights in the model, encouraging simpler models that generalize better. So again, the goal here is to generalize better. And let's get into how this works when we apply this technique. On the left, we see weights from a model trained with L2 regularization. Looking at these weight magnitudes, we have 4.7, 3.8, 5.2, negative 1.9. These are relatively large weights that can lead to complex model behavior and potentially overfitting. So we apply L2 regularization with a lambda value of 0.01 shown on the right. And we notice how dramatically the weights change. The same parameters now have much smaller values. So this shrinking effect is the point of L2 regularization. It's the hallmark of it at work. The mechanism behind this is shown in the equation at the bottom. L2 regularization modifies our loss function by adding a penalty term. Instead of just minimizing the original loss, the optimizer now minimizes the original loss plus lambda times the sum of all the squared weights. So notice that by squaring the weights, we are penalizing based on their magnitude, regardless of whether they are positive or negative. A weight of 4.7 and a weight of negative 4.7 would both contribute the same penalty. This creates a mathematical pressure that pushes weights toward similar, smaller values, rather. During training, the optimizer must balance two competing objectives, fitting the data accurately, which might require larger weights, and minimizing the penalty term, which requires smaller weights. So the lambda parameter kind of determines how strong this balancing pressure is. And the result is a model that trades off a small amount of training accuracy for much better generalization to new data. That's it for this section on specific hyperparameters.